Hi, this is a supplementary physics lesson for chapters sections 19.1 through 19.3 in your textbook, electric fields. So I'd like you guys to read over those sections of the textbook. I'm just going to hit on the major points, and in conjunction with the crash course physics video on electric fields. You should have watched that before this. That was assigned Friday, due today. If you have not watched that video, go ahead and watch that video first, then come back and watch this one, okay? So, points to hit on here. What are electric fields, okay? Electric fields are a way to determine the strength, okay, of electric forces at any point based on a charge. And so we do that by establishing with these lines, this graphical method, the electrical field, okay? Now the strength of that electrical field, they have two equations in the book, okay? It's going to be our electric force per charge, okay? Per unit charge is how the electric field is expressed, okay? If we substitute Coulomb's law into that, they explain this derivation here. So let's just take a look at that. The electric field strength, okay? So what does that tell us here, okay? It tells us, okay, big Q being the big charge, and they said it has to deal with a little q out here, a small charge, and one of the points of this small charge q out in space here, away from our big charge, it says it has to be small enough. In fact, we assume that it's so small it doesn't affect the electric field of this charge here, okay? Now if we have another charge, a big charge, we know that they interact, okay? That they either attract or they repel each other. And that would be the same case between a large charge and our small test charge. But what we're saying for discussion's sake, okay, that this charge is so small that it does not affect. All it does is it feels the effect from other charges, okay? So if that's being the case, okay, the smaller that charge is, as the smaller it is, the larger force, okay, that's exerted from, our big charge, okay? Here, the larger the big charge is, the stronger the electric field strength, okay? But we noticed this is the field strength at any point. The further we get away from that big charge, okay, the smaller and smaller our field strength gets, okay? And so electric force, just like gravity, diminishes with the square of the distance away from the particular charged particle, okay? And so we draw electric field lines in, and the book has rules for that in a call-out box on the right-hand side of page 415, okay? Electric field lines, okay, what is it? They express in vector form, okay, the direction of the electric force, either toward or away from a charged object. And we say the convention is we draw them away from a positively charged object. We draw the electric field lines toward, they terminate at a negatively charged object, okay? And we notice they proceed radially outward or radially inward, okay? Just like gravity, it's a central force. It acts towards the center of the charged particle. It acts away from the center of this charged particle, radially, it's kind of hard to say, outward, okay? So for a test charge Q, a small q, that's so small, it doesn't affect the field at all. It just feels the effect from this large one. The force that it feels is an extension of this vector radially outward. So that test charge, because they're both positive, would feel a force radially outward in that direction away from the large positive charge. Okay? And so we notice, though, that vector, okay, it expresses the direction, but because of our distance, okay, this field strength out here is going to be less than it is here. Okay, and that's going to be less than it is here. And we notice as we get closer and closer to the object, these field lines get closer and closer together. They scrunch in toward that object. Here, as we get closer to the negative object, these lines get closer and closer together. So that's one of the another points of these electric field lines. The closer together they are, the larger the electric field strength at that point. Okay, out here they get further and further apart. The field strength is less. It's a graphical way, a visual way to see that force. Okay, and I wanted you to do that lab on magnetism, mapping the magnetic field, because magnetic fields and electric fields are similar in many ways, especially when we have two charges involved. Okay, they're a little bit different, but they're similar in many ways. Other things that the field lines express. Now we notice, and they mentioned this in the video, electric field lines can never cross. Okay, they originate and proceed outward from a positive charge, and they terminate at a negative charge. Okay, they may go off for quite a while, but they will eventually terminate at a negative charge. Okay, and so what does that tell us? Just like gravity, you know, we said electrostatic force is very similar to gravity. It has no limit to the distance at which it acts. It acts at any distance, okay? It's just that the strength gets weaker and weaker and weaker, okay? But there is an effect, a force, okay? But it has no limit to the distance over which it acts. Okay. By the way, because of that concept that all field lines must start at a positive and end on a negative, and that the universe has no electric field lines that just kind of wander off by itself. They don't have this field line that just kind of goes up forever and ever and ever and never finds a negative charge. They all find a termination because of the conservation of mass and energy, and we also have the conservation of electric charge. Okay, there are only so many charges in the universe, and they are balanced charges. Okay, that they all terminate somewhere. Okay, all these lines have a home to go to, one place or another. Okay, which is kind of an interesting concept to think about when you think the massive size of our physical universe. It's kind of cool how God has created that. Okay, so we can notice that, and we've done that with Coulomb's law. What is the force between two charges in here, or what is the electric field strength acting on our test charge a certain distance away? And we also know, and through their videos, that okay, these lines will, between two charges, they will form electric field lines that join each other. Okay? And so, this particle here is pushed out radially from the positive charge, but it's also affected by this negative charge. It is pulled inwardly, radially, to that negative charge. Okay? And through vector addition, we can say the net force acting on that charge will be the addition of those two vectors. Okay? They do an awesome job diagramming that and explaining that and showing the electric field lines in detail and the vector addition at the top of page 415. Make sure you go over that figure 19.4 in detail and understand what's going on. They do a great job explaining that, what I've just drawn here. And it brings us to one of the last points with electric field lines. Okay, what are they showing us? They're showing us the direction of the field strength, or of the magnetic field at any point. Okay, so if we're talking about what is the direction of the magnetic field at this point where our test charge Q is, it's the addition, it's the vector addition of the interaction, the field strengths, the electric fields of these two charges. We draw on the vectors how that charge is repelled by the positive, attracted to the negative, and we've added them together. And what is it? It's a line at that point that is tangent to our curve, to our electric field line. It's tangent, parallel to it at that point. So what does that mean? It means at this point in the electric field, the field strength is pushing a test charge that way. At this point in the electric field, it is pushing it, it is doing it that way. At this point in the electric field, it's tangent and parallel to that point. It's doing it that way. Okay? So it's telling us if we threw a test charge on there in our electric field here and it landed there, what would happen? It would get pushed that way initially. Then it would get pushed. It would eventually, it would follow this curved line until it hit that positively charged or negatively charged object there. So it shows the direction. The force, the electric force, is pushing it inside the electric field. Okay, gives the direction. Okay, it also is going to give the physical path that it would take if it were to allow to travel. Okay, and then we'll get into this tomorrow. Okay, depending on where it is, okay, tells us how strong that force is. So we notice that if we plopped our test charge back here, the electric field lines are close together, the force would be larger. Okay, it would push that particle out at a higher rate of speed than when it got out here between the middle of them. The field strength is less. There's less force on the object. There's less acceleration. That test charge will actually slow down. It'll keep going though, and then as it gets closer to this object, it will speed up again. Okay, so that's kind of an interesting development there. Kind of interesting, just because the field strength varies with the distance. Okay, we'll get into that more tomorrow. So I hope that helps. You have, I'll give you on the email your chapter review problems. Only one of them is a math problem. You have to determine which of these field strength equations to use to get the field strength of that problem. Okay, so you could use either way. It's easy to determine. Depends on what given information they give you. The clue in there is if they don't give you the distance, hey, you gotta use that other one. So I hope that helps with your assignment today. I'll give a text message or an email if you have any questions. So long for now.